Hi, it's my pleasure to present CroCo V2, the work that we did at Neverlabs Europe on improving cross-view completion pre-training towards state-of-the-art performance on stereo matching and optical flow. Self-supervised learning, such as contrastive learning or mask image modeling, has proven successful in many high-level semantic tasks like image classification, object detection, or semantic segmentation. In this paper, we study whether self-supervised learning can provide benefit for dense matching tasks like stereo or flow. There are several challenges. First, most self-supervised learning objectives are monocular, while these tasks are binocular. Second, state-of-the-art stereo and flow methods leverage task-specific designs, such as coarse volumes. They are too heavy and thus require additional tricks, like coarse-to-fine schemes. These task-specific designs hinder the applicability of task-agnostic training. In this paper, we build upon the recent cross-view completion, or CroCo, to pre-train a simple binocular architecture composed of a monocular encoder and a binocular decoder. CroCo extends mask image modeling to pairs of images depicting the same thing. Filling in the mask content requires to implicitly understand the geometry and relative viewpoints between the two views. We show that this model can be effectively fine-tuned on stereo or flow, leading to state-of-the-art results on these two tasks. This is achieved with the same architecture for both tasks, despite the absence of any common design like closed volumes. Let me first provide an overview of CroCo during pre-training. The first image is split into non-overlapping patches, and a high ratio of them are masked. The visible patches are encoded into a latent representation with a VIT encoder, and then padded with masked token to account for the hidden patches. The same encoder is used on patches from the reference image. A decoder then receives the encoded token from both images and uses them to reconstruct the masked part of the first image. In practice, the decoder is composed of blocks that alternate between self-attention and cross-attention. In this paper, we propose 3 avenues of improvements for CroCo. While the original CroCo paper uses only synthetic data for pre-training, we propose a pipeline to collect more than 5 million high-quality and diverse pre-training image pairs from existing real-world datasets. Second, we scale up both the encoder and the decoder. Third, we replace the cosine absolute embeddings that are added to the patch embeddings by a relative positional embeddings that are better suited for dense pixel-wise tasks of higher resolution. In this work, we rely on rotary positional embeddings, or ROP in short. Let me now give more details about how we collect CroCo pre-training image pairs from real-world datasets. These pairs must depict the same scene with different viewpoints. We propose a pipeline that allows to leverage some camera information contained in existing datasets, either based on structure from motion or external sensors such as LiDAR. In addition to the synthetic dataset of indoor rooms from the Habitat Simulator used in CroCo, we collect more than 5 million diverse image pairs from various scenarios. Indoor rooms with air kitchens, landmarks with megadepth, outdoor views with 3D Street View, indoor environments with the visual localization dataset. Once pre-trained, we keep these simple architectures with a VIT monocular encoder to encode each image, followed by a binocular decoder with self-attention and cross-attention. We use a DPT head to output the predicted disparity or flow and use a direct regression loss. Note that our architecture stands much in contrast to the well-established state-of-the-art that rely on coarse volumes and many other task-specific designs. We use the same architecture for both stereo and flow and name this method CroCo Stereo or CroCo Flow depending on the task it is fine-tuned for. We now compare CroCo Stereo to the state-of-the-art. Here are the results and some visualization for Middlebury. CroCo Stereo performs best on 6 out of 15 sequences. On Kitty, CroCo Stereo sets a new state-of-the-art. On ETH3D, we perform best at a threshold of 0.5 pixel and second best on other metrics. Finally, on the recent Spring benchmark, CroCo Stereo significantly outperforms the state-of-the-art. For optical flow estimation, here are some visualization of CroCo Flow on NPI Sintel. On the leaderboard, we are competitive while obtaining state-of-the-art results on Kitty and Spring. The pre-training data and code, as well as the code for stereo and flow, are available online. Thanks for your attention.